Hi, welcome back to Educator.com. For this lesson, we're going to talk about coordinate systems. The real numbers are great because there's an inherent order in them. Whenever we think about numbers, we naturally get a sense of progression. There's a natural progression, at least in the positive numbers. If we consider the positive numbers, it seems fairly inherent to us, I think, that the larger a number is, the larger its quantity represented is, and so the higher in the order it is, right? The number 1 is lower than 2, is lower than 3, is lower than 4. And if you're in between them, if you were to say 1.5, then you would be between 1 and 2, right? You would be greater than 1, but you would be less than 2 if we're looking at the number 1.5. So we've got a pretty inherent sense of an order that fits to the real numbers. Now, what if we want to expand that to the negative numbers? So if we want to consider the negatives, if we want to be able to have our order be usable not just on the positive portion, which makes obvious sense, we also want to be able to use it on the negative, then we want our negative and positive orders to agree. We want to be able to order the negative and positive numbers at the same time. So to make sure that they agree, we make it so that small negatives, the negatives that are closer to 0, are higher in the order than large negatives, which makes a certain kind of sense. A small negative takes less away, so it seems more reasonable that it is a bigger thing because it does less damage in a way. Not the best metaphor, but a smaller negative takes less away, so it's closer to being a positive than a big negative number, which takes even more away. So it makes sense that really big negative numbers come lowest, then small negative numbers, then 0, then small positive numbers, then large positive numbers. So this seems pretty darn reasonable, and it makes internal logic. There is an internal logic here. It doesn't contradict itself, so it seems like a good thing to run with. So we take this idea and now we'll use symbols so that we can denote it easily. We denote the order with two symbols, the less than symbol and the greater than symbol. So -1 is less than 0. 0 is less than 1. 1 is less than 2. 5 is greater than -12. -12 is greater than -47. So these properties are transitive. That's something we can notice. If A is less than B is less than C, then A is less than C as well, and similarly for greater than. This makes sense, right? If we've got -12 in between them, we can just sort of snip out the -12 and we will get 5 is greater than -47, and similarly over here, -1 is less than 1. So we've got the order, and we don't have to have all of the elements in the middle for the order to still be there. If you have difficulty remembering which way the sign points, does it point to the big number or does it point away from the big number? I like this mnemonic. I was taught it long ago and it really helped me learn it. So this sign, how do we know which way it goes? Is because we imagine it is an alligator. There is an alligator here, and the alligator is hungry. So the alligator is hungry. And because he's hungry, he wants to eat the biggest thing possible. So he says, I'm hungry. Give me big food. So it makes sense that the alligator is going to point towards the bigger object. The bigger the number is in our scale, the alligator will want to eat that one in preference of the other one. So the alligator is one way of thinking about it. The other one is just thinking that the wide part is always pointed at the bigger number, but I like the alligator mnemonic and it worked well for me, so there it is for you if you haven't heard it before. All right, less than, greater than. We can also talk about this in terms of variables. So if we know that a variable is less than 2, but we don't know the precise value of the variable, we could say x is less than 2. So that gives us the ability to use this order on a variable. We know that the variable is less than the number 2. We don't know what it is precisely, but we know whatever x is, it must hold true with this relationship. We call this kind of relationship an inequality because the two sides are not just equal. An equality implies there's equal on the two expressions. Inequality implies that the two expressions are unequal, and we know something about how they are unequal. So an inequality is going to be less than or greater than depending, and that's what where we get inequalities. If we want to say that the relationship might be equal, we can use the signs less than or equal and greater than or equal. These come from a merging of the less than, or the greater than, and the equal sign. We put these two things together, and together they spit out guys like this. That's where we're getting it, is it's the less than or greater than sign up top, and the bottom half is 1/2 of an equal sign. So that's where we're getting less than or equal and greater than or equal. So 1 is less than 2, and technically 2 is less than or equal to 2. It's true, although that would be one of those cases where it's sort of like, yeah, it's not a very useful thing to say, but it is accurate. All right, moving on. Now we can express this idea of our order that we've been just considering, this idea of order on the number line. The number line is a graphical representation of the order that the reals have inside of them. We build this out from the origin, the 0, to the left with negative infinity and to the right with positive infinity. And remember, I talked about this previously, but infinity is not actually a number in the reals, and it's not a number on the number line. It's just the idea of continuing on forever. It's that arrow that says just keep going in this direction. We never stop going to the right as we go positive infinity. We never stop going to the left as we go negative infinity. So we never actually hit those values because they aren't actually values. It's just the idea of keep going on forever. All right, if a number is farther to the right, it's greater. The greater numbers go on the right, the less numbers go on the left. So if you are to the right of a number, then you are greater than it. If you're to the left of a number, then you are less than it. So this number line gives us a really easy visual representation of that order we were talking about. And we can put down any number we want, right? Here is 1.5. Here is, 2.5. Here, somewhere around like here-ish is pi, and we could talk about, say, 4.7 over here, and so on, and so on, and so on. We can, this thing is, all of the real numbers, all of these very fine-grained numbers are fit in between the obvious landmarks of the whole numbers. The integers just make up landmarks, but the real numbers is that whole continuum, that fine spread of numbers. They're tiny, tiny little numbers. 2.888 versus 2.8889, right? Tiny, tiny differences, but still different numbers. All right. Ordered pairs. What if we want to talk about more than one number at a time? Say we want to talk about 2 numbers at once. Consider this motivating example. We survey a number of households and we ask how many dogs and how many cats each household has. We get these answers back. 0 dogs and 0 cats. 2 dogs and 0 cats. 1 dog and 2 cats. 0 dogs and 3 cats. So these are all of our answers, and we can write them out as we just did. But, I'll be honest, I'm lazy. I'd like to find a way to be able to do this with less space, to be able to do this having to write less. So here's a useful place to bring up ordered numbers. So we really only care about the numbers, right? 0 dogs, 0 cats, yeah, okay, but really all I care is it was 0 and 0, right? So as long as we know which number represents which animal, we can throw away with the words. So we can create ordered pairs because we have to know what order it came in. Did it come in dog, then cat, or cat, then dog? So we set up an arbitrary order. We set up dogs go first, cats come second, and then we can convert all of these words into just 0, 0. 2, 0, 1, 2, 0, 3. This takes much less space, much less writing, same info. So if we want to talk about an ordered pair, some ordered grouping of numbers, it's parenthesis, blank, comma, blank, just numbers going in those blanks, and we close it with parentheses. Now notice there is some slight confusion with intervals in the reals. We talked about this before. If we had intervals in the reals, we might have shown it with parentheses. So there is the possibility for a little bit of confusion when we're dealing with talking about ordered pairs, when we're talking about a point in 2 dimensions, but almost always it's going to be obvious if we're talking about an interval or if we're talking about a pair of points. If we're talking about a pair of numbers, if we're talking about a point. So don't worry about getting these two things confused. It's almost always going to be totally obvious in the question which one is implied. It's very hard to get these two confused when we're actually working on problems because it will be very clear from the context which one is meant. So don't worry about that. Even though they use the same notation, we'll always know which one is actually being implied when we're working. So this idea of an ordered pair allows us to talk about two numbers at the same time. Depending on the problem that we're working on, the relationship between the two numbers will change. So, in one problem, the relationship might be dogs and cats. In another problem, it might be, the height of a ball and how many seconds we've gone in time. And in another problem, it might be the number of houses bought in a certain span of time and the cost of all of those houses together. So it's going to be totally different from problem to problem. And potentially the two numbers could be completely unrelated, right? It could be the number of words in this lesson and the number of grains of rice that is currently sitting on a bowl in some restaurant in California, right? They're completely unrelated numbers, but we can just put them together if we so desire. We won't want to do that in our problems because it won't help us understand anything, but it is a possibility. The two numbers don't have to do with each other. In all of our problems, though, they will be somehow connected, and the problem will show us how they are connected. It should also be pointed out that ordered pairs of real numbers can't be put into an order like we did with reals. So the reason they're called ordered pairs, so ordered pairs is because location in pair matters, right? So we care about who is first, we care about who is second. It has a different meaning if we swap those two numbers. It's a different meaning if the second number comes first and the first number comes second. So the location in the pair matters. But when we talk about in order, like in the real numbers, I'm talking about, being able to say what place in line, right? Who is closer to the front? Who is farther ahead is what I'm talking about with this idea here. So this idea here is different than the ordered pair idea. So while they are called ordered pairs, they can't actually have an order. So we could compare the first values and we could compare the second values, but we can't actually say that an entire pair is greater or less than another pair. Consider these three pairs: -10, 10, 5, -5, -3, 3. And what the heck, let's also consider 0, 0. Right? None of these pairs are equal because none of them are the same thing. To be equal, they have to actually be the same thing. -10, 10 is not the same as 5, -5, not the same as -3, 3, not the same as 0, 0. None of these things are equal to each other. But we also can't put them in any order, right? Who gets to be the biggest one? -10, 10? If -10, 10 is the biggest, what about 10, -10? Would that be bigger or smaller? And if it's bigger, why is it bigger than -10, 10? And if it's not bigger and it's not smaller, then it must be equal if we're going to go with that idea of order that we have in the real numbers. So any possibility of putting them in, this comes first, this comes second, this comes third, that's not possible when we're talking about ordered pairs. We can give them out, we can give out a variety of them, but we can't really say anything about their location and where they came. That's just something to notice about them. They are ordered because we care about their first and second values. We care what order the values come in the pair, but we can't put them in an order as in saying this one goes here and then followed by this one and then followed by this one. That's not a possibility. All right. This gives us the ability to talk about a two-dimensional surface, a plane, where we can plot these ordered pairs. So we visually represented the reals with the number line, and now we can represent our ordered pairs with the plane. So we call it the plane. To do this, we cross a horizontal number line with a perpendicular vertical number line. They both cross at 0. So down here at this little right angle is 0 on both the horizontal axis and the y-axis. I don't know if you can quite see that. That should be an arrow pointing down there. So this gives us the ability to plot points because now we can deal with both parts of our values, right? Comma, value, comma, value. We can give one of the values we can put on one axis, and the other value we put on the other axis, and where they agree, we plot as a point, right? So that way we can talk about 3, 2 being different from 3, 3, because that's 3, 2, and here is 3, 3. So we're able to talk about totally different locations by having this plane. We can put down both pieces of information from our ordered pair, both the first value and the second value, and that's really great for us. We call the point in the middle, we call that point of intersection of the two number lines the origin. That's the origin. It is 0, 0. By convention, the first number in an ordered pair always goes by the horizontal. So if it's first comma second, then the horizontal is always going to be based around, the horizontal location is always based around the first value, and the vertical location is always going to be based around the second value. So once again, if I had something like 2 comma 4, then the first value, we go here to 2, and then we rise up until we hit 4. So 2 comma 4. So this convention is an important convention to remember. First thing always gets placed to the horizontal. Second thing always gets placed to the vertical. And sometimes it will change. When we start working on functions, we'll often call the vertical axis the f of x, or the function axis, the value from the function. But normally we're going to call the horizontal axis the x-axis and the vertical axis the y-axis. Why do we do this? What's the reason for it? Well, often we talk about points x, y because they're coming from some equation y equals blah, 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 involving the number x. Right? So we plug in some x, we'll get some value here, and that will give us some value y, and then we'll put them in. So our y will be our second value, our x will be our first value. So often we just associate x with being the horizontal, being that first value, and y with being that second value, being the vertical value. It's not always going to be the case. It could be something different, but that's normally what it's going to be. Also, if you have difficulty remembering who goes where, is it x then y, is it y then x, who's horizontal, who's not horizontal, here's my mnemonic for you. So remember, it's going to be x comma y, because like the alphabet, right? So it's x comma y like the alphabet. But not but, x comma y like the alphabet, W, X, Y, Z, so X, Y, that's the order it comes in. And then when we read, you read left to right, which is to say horizontally, and then you read up, down, right? You start high and you go low, which is to say vertically. So when we do reading, just like normal reading, we start off reading horizontally, at least in English. We start off reading horizontally, left to right, and then after we've done that, we do up, down. We do vertical motion. So it makes sense that x, y, like the alphabet, right? The alphabet goes like that. And then if we're also continuing to talk about the alphabet, left to right is how we read first, and then up, down, vertical. So x will go with the left, right, and y will go with the up, down. So that is the mnemonic I'm going to give you for this. It's maybe not the perfect mnemonic, but you really have to just sink this one in because you have to be able to be ready to see these things over and over and over. The plane has many different names. Sometimes the plane is called the coordinate plane because we call these values, the first value and the second value, we call them the coordinates. Sometimes they'll also be called the x-coordinate and the y-coordinate, the horizontal coordinate, the vertical coordinate. We also call it the Cartesian plane. Why do we call it the Cartesian plane? Because René Descartes, I'm not very good with my French, sorry René Descartes. René Descartes was a French philosopher and mathematician in the early 1600s who did a lot of work with talking about stuff in the plane, did a lot of really great math, and so it is named in honor of him, the Cartesian plane, from his name Descartes. So Cartesian plane is just coming from his name Descartes. So that's another name for it. Coordinate plane, Cartesian plane, and one more way you can call it, which you probably don't see until you get into college much, but you will see it now and then if you get into advanced math in college, R2. We'll talk about it R2 because what we've got is we've got one real line crossed with another real line. So it's R and R, or two R's put together, R2. We can also talk about quadrants within the plane. Quarters of the plane. If we want to be able to talk about a point being in one of the quadrants, the four quadrants of the plane, we need to know where each quadrant occurs. So we start off with where both coordinates are positive. So that is quadrant 1, where the x value is greater than 0 and the y value is greater than 0. Both values are positive. So positive and positive. Then from there, we work our way counterclockwise. Why do we work our way counterclockwise? There's no good reason. We just chose one because, humans had to choose one at some point, and it just became the way we do it. Sorry. If you'd rather it was in clockwise, yeah, it's a little confusing, but maybe it's just as maybe clockwise would be just as confusing as counterclockwise. It's just the way it is. Sorry. So we go counterclockwise from here. We start 1 in the positive location, positive, and then we go to 2. So at this point, we've crossed over the y-axis. We've gone over the place that is 0 on the x-axis. So now we are in negative x land. So it is going to be negative on the horizontal, but still positive there. And that's quadrant 2. After that, we move on to quadrant 3. So now it's going to be negative because we're still on the negative side of the x-axis. And now we've made it onto the negative side of the y-axis because we've dropped below the horizontal axis. So here it's going to be negative and negative. And then from there we finally go on to quadrant 4, finishing things up. And now we've managed to flip over to being the positive side of the x-axis, but we're still in the negative part of the y-axis. So it's positive here and negative here. If a point is on one of the coordinate axes, or both of the coordinate axes, it's not in a quadrant. It isn't in any quadrant. It actually has to be not on the lines building our plane. It has to actually be completely inside of the quadrant to be considered in a quadrant. If it was on a mid-ground between quadrants, we wouldn't really have a good way to talk about it. I mean, we could say it's between quadrant 1 and quadrant 2, but instead we just say it doesn't have any quadrant unless it's actually smack dab inside of a quadrant. We can continue this idea to an even larger level. We can take these ideas and start running with them. If we want, we can create ordered triplets. So before in 2 dimensions we had x comma y, now we can go to 3 dimensions and we can go x comma y comma z. To visually represent this, we have our same perpendicular thing, right? We've got that same sheet that we used to have here. That same plane is back here. But then, in addition to that, we create another vertical axis. So it's a little hard to see because we're trying to represent a 3-dimensional object with a 2-dimensional thing. But we've got one line, and then a third one coming out of them. Right? So we can sort of see it from my fingers in this not so great way. We call this 3-dimensional space. Space is the word we use for it because it's just like the space we live in, right? We live in a 3-dimensional world. You can go forward, backward, left, right, and up, down. It's through the combination of those 3 major directions, which turns into 6 if we include the positive direction and the negative direction, that we were able to move through the world we exist in. So it's just like the space we exist in. Since it's 3 real lines put together, we call it R3. This course won't explore much in 3 dimensions, but it's an interesting thing to think about, and we will have a little bit of stuff on it. If we want to, we can take these up to even higher dimensions. We can continue this idea and run up to as many dimensions as we want to have. If we have n dimensions, we call it n-dimensional space, which we might also refer to as Rn because it is R, the real line, put n times together. We can represent places in this n-dimensional space as ordered groupings of n numbers, right? If we are in 2 dimensions, we go x comma y. If we are in 3 dimensions, we go x comma y comma z. If we're in 4 dimensions, we just put in another one to that grouping, x, y, z, w, or some other symbol. And so we can keep running this up to as many symbols as we want. We can have as many different coordinate locations as we want for whatever our Rn. You give me an n and I can make a coordinate that has that many n slots, that has n many slots in it to give us a coordinate system. However, there's no good way to visualize higher dimensional spaces like this. We live in and we're adapted to exist in a 3-dimensional world, right? It's very hard, if not completely impossible perhaps, to represent anything higher than 3 dimensions in a way that we can really see and intuitively grasp in a single picture. So this course isn't going to discuss higher dimensions, but I think this stuff is really, really fascinating, and it's an interesting thing to ponder. If you think this is really interesting and you're like, wow, I actually really want to think about this more, there's a book called Flatland. That's a pretty fun book. I actually haven't read it, but I know about it. Flatland, which is a book about 2-dimensional beings coming to live in a 3-dimensional world and what their experience is like and various things like that. So if you think these ideas are really cool, go check out this book, Flatland. Pretty cool stuff. All right, example 1. If we want to order 5, 18, and -7, how do we order it? Well, first off, we can just go, okay, well, that's pretty easy, right? 5 is less than 18, and since negative is less than positive, it must be -7 is less than 5 is less than 18. There's our answer, right? But that's not the best way to approach it. Instead, it might be useful to be able to go, well, let's see if we can see it visually first. So instead, we make a number line. So we make a number line, and we won't be very careful about giving it a scale, but we can still give it a sense of where these numbers are, right? Well, here's -7 somewhere over here on the left side, and then 5 is kind of closer to 0, and then 18 is way out farther to the right. And so we see this in the order. It goes -7 to 5, and then 5 to 18, which is exactly what we've got right here. So for this kind of problem where we're just ordering 3 numbers that we can actually see, not that useful, but it becomes really handy when we're working with numbers that we can't actually lay hands on. We don't know what the value of the number is. For example, if we know that a is greater than 0, and we want to order a, 2a, and 3a, it becomes really handy to think of it in terms of this number line, right? We don't know where a is, but we know it's somewhere to the right of 0 because it is a positive number, right? A greater than 0 implies that a is a positive number, so it's somewhere over here. Well, if a is over to the right, then 2a would just be adding on another a, right? So we'd get to 2a because that would be a up. And then if we want to get to 3a, we just add up another one. Now we see what the order is. It goes a to 2a, and then 2a to 3a. Now we've got our order. So we can see visually what might have been difficult to talk about in a really analytical way with just symbols. By being able to make a picture, it becomes easier for us to understand. Great. Next example, now we're going to really use this idea of using a number line to understand what's going on. If b is less than 0, we want to order b, 2b, 3b, -b, -5b, and 0. So what we do here is we set up that same number line, and let's arbitrarily place a 0 somewhere. Now the first thing we need to do is we need to, since everything with the exception of the 0 right here is in reference to b, we want to be able to say, well, where is b? We don't know its precise location, but we know which side it must fall on because we know b is less than 0. Since b is less than 0, that's the same thing as being negative, so let's just toss it here. So b is less than 0 right now. Now if we go 2b, well, 2b is going to go in the same direction as the original one, right? It's not going to be that b is at below 0 and then 2b hops up to 0, right? We're going to continue to go backwards by another b, so now we'll be at 2b. We do that again and we get to 3b, right? So there's b, there's 2b, there's 3b. So we've ordered the first all the negative numbers. Now what happens if we look at -b? Well, -b is going to take this same distance here and it's going to flip it here, right? So what had been here to get to b will instead flip to -b, right? If we take 2 and we put a negative on it, we get to -2. So we flip to the opposite side of 0, but that same distance away. So b now flips to -b. If we want to look at -5b, then it's going to be a total of 5 b's up from 0. So we will be at -5b here. So now we see what our order is. 3b is less than 2b is less than b is less than 0 is less than -b is less than -5b. So what would otherwise be a very difficult problem for us to solve if we were just trying to do it all in our head, trying to think purely in terms of the numbers going on, it becomes a lot easier with a visual representation. One other way, if you had real difficulty with this, is you could say, well, okay, I don't know what b is, but we could use a hypothetical number, right? We could plug in b equals -1 and try that out. So we try out b equals -1, and sure enough, b less than 0, that checks out with all the requirements that we have on b so far. So it's a reasonable hypothetical number to choose. If that's the case, then b equals -1, 2b would equal -2, 3b would equal -3, -b would equal -1, so +1, -5b would equal -5 times -1, so +5. So we get that same ordering going on. Exact same thing going to happen if we try out a hypothetical number, but I really like the idea of being able to see this visually, so that works out great, really well for this sort of thing. We can get a good understanding of what's going on. Third example, plot these points. So we get all these points. To plot them, we'll need a plane to start off with. So we draw a vertical line. We draw a horizontal line. We get our horizontal axis and our vertical axis now. Let's mark off some sort of scale. 1, 2, 3, 4, 5, -1, -2, -3, -4, -5, 1, 2, 3, 4, 5, -1, -2, -3, -4, -5, -6. So we've got a scale going with it now. My scale's not perfect, but it's pretty good, right? I'm not absolutely perfect in me drawing on this thing, but it's not a terrible scale. It's good enough for us to get a good idea of where these would show up. So plot the points 0, 5. So 0, 5, remember, first goes to the horizontal, second goes to the vertical. So 0, 5 is going to be 0 horizontally and up 5 vertically. So 0 horizontally, we're right here, and then up 5, 1, 2, 3, 4, 5. Here we are at 0, 5. 5, 0, forward, 1, 2, 3, 4, 5, and we go up 0 because it's 5, 0. So here we are at 5, 0. If we want to do -1, 3, we go -1 horizontally and up 3 vertically, 1, 2, 3. And 4, -3, we go over 4, 1, 2, 3, 4, down 3 because it's -3, -1, -2, -3. And we've got all of our points plotted. Remember, first value always goes to horizontal, second value always goes to vertical. Final example, let's say x is 2 and y is -1. Now we want to plot the points x, y and 2x, -3y. And we also want to say what quadrants they're in. Then after we do that, we'll start off, we'll say that a is less than 0 and b is greater than 0, and then we need to say the quadrants of a, b and -a, -b. So first off, let's do plotting the xy and 2x, -3y. So if x is, we know what the value of x is, we know what the value of y is, we can actually figure out what x, y is, right? We just swap out the numbers, we substitute. X is 2, so we get 2, y is -1, and there is x, y. If we want to figure out what 2x, -3y is, then we swap out for the values, and we'll get 2 times 2, and -3, pardon me, let me move it down to the next line. So 2 times 2, -3 times -1, which is the same thing as 4, +3. So there are our 2 points that we're looking to plot. We draw our coordinate axes, quick toss on a scale for it to have. So we have places to plot. We go over 2, down 1 to -1, and there is 2, -1. We go over 4, 1, 2, 3, 4, up 3, 1, 2, 3, and there is 4, 3. So 4, 3 is in the first quadrant, and we count counterclockwise 1 to 2, 2 to 3, 3 to 4, and so this is in the fourth quadrant. So fourth quadrant, first quadrant, and there they are plotted. What if we wanted to figure out what a is less than 0, b greater than 0, what quadrant it would be in? Well, we don't actually know what A is. We don't actually know what B is, but we have enough information to figure out what quadrant it's in. So if A is less than 0, it's a negative number, and if B is greater than 0, it's a positive number. So if we want to figure out what A, B is at, well, if A is a negative number, then it's going to be somewhere over, here-ish, right? We don't know what the precise value is, but we're just being rough so we can get a sense visually of where it goes. And B is going to be a positive number, so it's going up. Remember, positive this way, negative this way, positive this way, negative this way. So it goes up, and so B is going to be somewhere here. Who knows where it is specifically, but we're going to have A, B somewhere in this area. We have no idea what the specific values of A and B are, but we know that it's going to have to fall in there because we know that its x-coordinate, its horizontal coordinate is negative. It's on the left side of the vertical line. And we know that its vertical coordinate, its y-coordinate, is positive, that it is on the top side of the horizontal line. So we know that we're somewhere in this quadrant, which is quadrant 2. So we are somewhere in quadrant 2. If we want to figure out where negative A, negative B is, well, if A is here, then it must be the case that negative A is over here. If B is here, then it must be the case that negative B is down here. So we put the two together, and negative A comma negative b. Who knows if it's going to be at that specific point, but we know from this logic that since it was previously negative horizontally, it's going to be positive horizontally. Since it was previously positive vertical, it's going to be negative vertically. So that drops us into this quadrant down here, so we must be in quadrant 4. So we get quadrant 2 and quadrant 4 from the 2 points for this. All right, hope you learned a bunch. Hope everything is clicking back into place and you're remembering everything that you need so you can really hit pre-calculus and get a great understanding of what's going on here. We'll see you at educator.com later. Bye.